Okay, welcome again, everyone. Thanks for your interest in the OsmoDevCall. Tonight, I will be presenting about some exploration with some practical demos and so on about eUICCs and eSIM using open source software tools like pySim, lpac, and osmo-smdpp. Before we go into that, I will do a rather brief, hopefully, review of or introduction into SIM cards and eUICCs and eSIM profiles. I'll try to go through this rather quickly so we can focus on the practical parts. I still think it's useful to cover some of those basics for people who are not working with this all the time or not familiar with it to that extent. So, yeah, so where do we start? Well, we start by increasing the size, I guess. Oh, it's not actually possible here. Okay, never mind. Not very familiar with this presentation system. So, classic SIM cards were introduced with GSM technology. That's the 2G cellular network technology, first deployed in production in 1991. They were single-purpose smart cards, and the fundamental purpose of every SIM is to store configuration data, store contacts and SMS, at least back then. And first and foremost, it's a secure element. I guess that term didn't exist at the time. Today, people would want to call it that way. That holds the secret key material for the authentication of the subscriber, and the unclonable nature, or at least most of the time unclonable, if you look at the history of the SIM card, is sort of protecting the operator's business because if people cannot clone the SIM card, they cannot clone the key material, and therefore the one and only holder of the SIM card is the one subscriber that can authenticate as this particular subscriber to the network. Later on, with the advent of 3G networks, the so-called eUICC was introduced, the Universal Integrated Chip Card, which is a multi-application smart card platform, and the eSIM, the UMTS subscriber identity module, became an application, so a piece of software that runs on the eUICC. And later on, with voice over LTE in 4G networks, an additional optional application called eSIM, the IMS subscriber identity module, was introduced. And then this basically means you have the physical card that you have is called a eUICC. And then you have applications such as the eSIM or the eSIM running on that card. Fundamentally, the purpose didn't really change so much. We still have storage of configuration data. It has gone a bit extensive it was a lot of bloat, you could say, in terms of parameters. So by now we have thousands of parameters in hundreds of files on such a eSIM application, or all of these applications running on the card. And it still holds the secret per subscriber key material. The key material and the authentication algorithms changed over time compared to the earlier classic SIM card, but fundamentally it's still the same. And even though it's a multi-application chip card, of course, you as the end user cannot install additional applications. It's only the card issuer, which is the operator, who can do that. Then last but not least, we come to the eSIM, which is the topic of tonight. And in the eSIM, now the idea is that the subscriber identity module, the eSIM and also eSIM and other parts, are virtualized. So we're talking about something called an eSIM profile, which contains all the information that your classic eSIM with optional eSIM contained. And this virtualized SIM, now called SIM profile, can be downloaded over the network and installed on something called the eUICC, the Embedded Universal Integrated Chip Card, which is sort of a bit of a misnomer, because in most cases it's not actually a card, but it is a chip that's soldered onto a circuit board. So calling this a chip card is sort of a bit, yeah, well, you see the legacy there. Now, this eUICC is also itself, of course, a multi-application chip card, even though it's not in card form factor most of the time. And it has key materials and so on, which we will look into some detail, which allows you to install or allows operators to install signed and encrypted virtual SIMs called eSIM profiles on this device. And eUICC can hold one or more of these SIM profiles. How many depends on the specific implementation and how much flash memory there's available. There's some that can only hold a few profiles, but some others can hold up to 10 or even 20, depending on the memory requirements. Of course, not every profile has the same size. It depends on how many files are populated and how large those files are. So there's a bit of variability in how much you can install on that. At least most, if not all, currently, like present day eUICCs, only one of those profiles can be active at any given point in time. Later eSIM specifications also introduce the concept of multiple concurrently active SIM profiles. I personally haven't seen any such eUICCs yet, but they might already exist. At least specification-wise, the latest versions permit something like this. The reason for this is then to replace basically, I mean, think of like a classic high-end smartphone. It typically had 2, sometimes even more SIM slots. Now today, maybe it's more common to have one physical slot and an eUICC. So in the future, maybe there will be devices that have only an eUICC, but still 2 modems inside for 2 different networks. And then you can have 2 eSIM profiles active on one eUICC, each of the modems using one of those profiles. Now, what is a SIM profile? As I said, it's sort of the virtualized uSIM plus iSIM plus other things. And that means the content of the file system, so all the potentially hundreds of files with their many parameters and all of their content. Then the authentication material, mainly the K and OPC, is the name how those keys are called. Also the specification, which algorithm to use and what algorithm parameters to use, millinage or TUAC, or there's yet another one I slipped my mind right now. But there's different algorithms. Also, there's the 3GPP test algorithm, the XOR algorithm, for example. And each of those has different parameters, and all of those parameters are also part of the SIM profile. Then there's key material for OTA access, so the way how operators do over-the-air access to SIM cards, where they can reconfigure things in the SIM card or install additional applications and so on. Then, of course, all the pin unblocking code, the PUC, the ADM pin, if there is one, by which the operator can configure or get elevated privileges and configure bits and pieces on the card. And then also any of the SIM toolkit applets. So basically anything that traditionally was stored on a UICC now gets sort of aggregated into a package that is called the SIM profile. And this format is specified in the eUICC profile package specification that used to be published by the SIM Alliance and that has recently been renamed into Trusted Connectivity Alliance. So there's this interoperable profile format, sometimes also abbreviated SAIP, so the SIM Alliance Interoperable Profile, SAIP, even though it's not SIM Alliance anymore. And that is an ASN1 specification plus associated PDF document that describes how those profiles are built. And the point is that, of course, if there are many different operators issuing eSIMs and there are many different eUICC vendors producing the chips, there needs to be some interoperable standard by which such a virtualized SIM or an eSIM profile can be communicated between elements in the system. So how does this look like? Let's try to have a quick look at, where am I? 11. So there we go. So let's have a quick look at how such a profile looks like. Actually, I think I still have, just give me a second. So if we look at a profile, if you want to look for an example, basically there is a test profile that's specified for interoperability testing that is published. And in the pySim repository, I have committed this in the SMDPP data UPP for unprotected profile package. So there's two different of them, 2.1 and 2.3. Those are different spec versions. Of course, if you open that, it's just a binary file. You won't really see much in there. It's encoded in DER, distinguished encoding rules. So the first level of looking at something like this is, of course, that you decode the DER. So you can use tools like unbar, which basically decodes you the tree of the objects, but it's also not very useful yet. So what we have in pySim now is we can now import pysim.esim.rsp as RSP. The takes a surprisingly long time because it compiles the actual AS1 specification in the background. And now we can do something like with open, and then we open this file. Of course, now I have the backslashes in this file name that I don't want, so I have to remove those here. So now I've read the file into the UPP bin variable, and what I can do now is, actually I imported the wrong up there. I want SAIP. So I can then do something like SAIP dot, not so smart. Well, I could, the first step would be something like this, asn1.decode, and there is a PE. Now the question is, how was it called in the ASN1? So profile element is the individual element. Yeah, okay. So we can actually do profile element UPP bin. This will decode the first element in the profile sequence. It's a sequence of elements, and this is, we see it's a GSMA generic test profile. It has a certain ICC ID, and what kind of services are mandatory? Apparently none in this, and some other bits and pieces. There's, of course, a higher layer tool available for this, like in the pySim library for decoding this in a more meaningful way. I just need to find which one. I have this SAIP test.py. I should have typed that somewhere. So that basically goes through the list of profile elements. The first element is the master file. It has a header, and then we see the individual files that are configured in the master file, the pin unblocking codes, the pin codes. Then we have a telecom element that's for the df.telecom, like on a classic SIM card. Then we have a uSIM profile element with, again, its files like the uSIM service table and the IMSI file and so on. And this continues then to also CDMA SIM card files, optional CDMA SIM card files. So here the eSIM application with the IMS private and public identifiers, the domain, the eSIM service table, and so on. And this is, of course, now listing just the files. I could go one step further and also decode the contents of those files. but basically the library code in pySim exists to work with such profiles. So that's just very quickly how such a profile looks like. Let's continue for now before we get back to looking at this again. The eUICC now itself is a smart card chip. It has some higher requirements than a classic SIM or UICC. The security requirements are quite strict. We will look at this also briefly. And it also needs quite a lot of additional cryptographic functionalities. For example, elliptic curve digital signature, elliptic curve key agreement, X509 certificate verification, and all kinds of things that a normal traditional SIM or UICC has no idea about. I mean, a classic SIM might be doing DES and AES crypto, but public key crypto, and particularly elliptic curve, is not a normal feature on a classic SIM card. The electrical interface is just the same like before. The protocol is also the same. Yeah, and I said typically they are soldered on a board, but you can also get eUICCs in plastic chip card format like SIM cards before. Now, if we look at this in a schematic view, or logical view, the eUICC contains an operating system. Let's not look into the details there. The main building blocks now we have is the ECASD, the eUICC Certificate Authority Security Domain. Then we have the ISDR, that's the Issuer Security Domain root, and then we have one or multiple ISDP. So actually could also be 0, but then it's not usable. So every eSIM profile creates what is here called in this block an MNO enabled profile or an MNO disabled profile. So that's our eSIM profile. And every eSIM profile contains an issuer security domain P for provider, a mobile network operator security domain, and then all kinds of things like the file system contents, the authentication bits, the applets, possibly additional security domains, policies, and whatnot. And as said in this example here, we also see one profile is enabled and one profile is disabled. The security domains is just a very quick list. So the ECASD and the ISDR, there's one of them that's fixed. Those are created during the production of the eUICC. And then we have the ISDP, the provider security domain. And it's the representative, you could say, of the mobile network operator, or actually the SMDP, that's the provisioning server that downloads the SIM profile into it. And there can be multiple, as if each eSIM that you have on the eUICC will have an ISDP in the end. eSIMs come in 3 flavors. There is the M2M eSIM, the consumer eSIM, and the IoT eSIM. Those are completely separate eSIMs and completely separate eUICCs. Yes, they all somehow solve the same class of problems in different ways and with different guarantees and properties. You cannot interchange those. So you cannot use an M2M eUICC with a consumer eSIM profile, or you cannot use the software that's built for IoT eSIM with a consumer eSIM or something like that. Those are completely different systems, and we will only look at consumer eSIM today. So in the consumer model, there is a client-driven pull model. There was a comment that about 3GPP convolutions. Well, actually, in this case, it's not the 3GPP which is to be blamed, but entirely the GSMA. So GSMA is the operator club where all the mobile operators participate. It's unlike the 3GPP, where it's less operators and more equipment manufacturers and regulatory bodies and intelligence agencies that participate in the specification making process. So yeah, so the consumer eSIM uses a pull model because it's intended for end user devices for consumers, so like your smartphone at home. And in this case, basically the user of the smartphone is the one who decides which profile should be installed and which should be activated and deactivated and so on. So the let's say the controller of what is to be done is the human user in front of the smartphone. And that's what this consumer model is trying to represent. The actual download of the profile happens over HTTPS, over TCP/IP. and it has some additional elements that don't exist in the machine-to-machine eSIM model. Yeah, so there's just some differences we don't need to look at. So it looks rather complex if you look at this, but in reality, all that is needed really in a minimum configuration is the eUICC here. Then we have, that's your physical chip. And then we have this sort of yellowish block here in the middle, the lpac. That's the local profile assistant. That's a piece of software that runs in your smartphone or in your machine-to-machine device or whatever it might be, a cellular modem. And then on top here we have the SMDP plus, the subscription management and data preparation plus. So those three are really the minimum things you need in a configuration. Of course, logically here the EUM is the eUICC manufacturer. Of course, that must have existed because you have an eUICC, so somebody has manufactured it before. Likewise, if there is an eSIM profile, then somewhere there's an operator that actually issues that eSIM profile and that sort of has this subscriber in their HSS or HLR. To associate any kind of network service with that subscription. But technically, the eUICC, the LPA, and the SMTP Plus are the three things that are needed. And this is actually what I'll be demoing later today, where we use a proprietary eUICC and an open source LPAD and an open source SMTP Plus, so we can look at all the different protocol steps and so on. So before we go into that, let's just bit explore the eUICC, the pySim shell tool. I guess at least some of you will be familiar with it. It's a tool, a interactive command line tool to work with usually traditional SIM cards. But in this demo today, we will be looking at eUICCs. So a couple of months ago, we added support for eUICCs in the pySim code base. I'm inserting a normal consumer eUICC now in the smart card reader. That was what was making the noise in the background, and that has now been done. So I can now do, I can start pySim shell with this. And it detects on this card we have a eSIM. That implicitly means a profile must be active, otherwise there would be no eSIM visible. Then we have the ECASD, the ISDR, and an RAM applet, and that is something else again. So these two parts here detected on the card, this means it's an eUICC, and we can interface with those. So we can do select ADF ISDR. So we enter the issuer security domain root. And then we can check what kind of commands do we have here. And the application-specific commands are those that somehow relate to the issuer security domain. So you already see there's stuff like delete profile, disable profile, enable profile, and these are exactly well, self-explanatory commands, what you can do with profiles. Let's start with something basic. We do get EID. This shows us the EID, that's the eUICC ID, that's a 16-byte, so 32 hex characters, a unique serial number of the eUICC. So since eUICCs can have multiple eSIM profiles, and the ICC ID, which used to be the physical serial number of the physical SIM card, is no longer a unique identifier, because now the ICC ID identifies the virtualized SIM card, and a new identifier called EID was introduced as a unique serial number of the eUICC. We can also get some eUICC information. So there's eUICC info 1, which tells us something about a version number, and then which subject key identifier values are recognized as certificate authority by this eUICC. This is the subject key identifier of the public of the root certificate of the GSMA certificate authority for the consumer eSIM system. So only one of them, it's the same one for signing and for verification, and only one such certificate authority is accepted. That's the one that is operated by GSMA. I think it's subcontracted to DigiCert or some company that is in the business of operating certificate authorities. You can find all of that information on the GSMA website, including the root certificate. So then there's also info 2, which tells us a bit more. It tells us what is the SAS accreditation number of the factory that produced this eUICC, and you can actually again look up the GSMA website and download the PDF file with the certificate that this factory was accredited with, and you can see the exact physical address at which the card was produced, if that is something you're interested in. We also see here a bit mask of eUICC capabilities that I'm not decoding here, which tells us sort of which of the optional features this eUICC supports. For example, earlier eUICCs don't generally support 5G standalone and the related df.5gs directory and files on in eSIM profiles. Later ones do support this, and this is something that would be expressed here. We also see the profile version 2.1.0. That refers to the SIM Alliance or Trusted Connectivity Alliance interoperable profile format. So we know that this eUICC supports eSIM profiles encoded in version 2.1.0 of that interoperable profile spec. Yeah, and we can also do list notifications. Well, there are no notifications pending here on this. And there's also get profiles info, which will tell us which profiles are on this card. Right now, there is exactly one profile from eSIM.me. That's the vendor of this SIM card, of this eUICC. There's exactly one profile, and it's enabled. Now, for example, I could do disable profile --help. I don't recall the exact syntax. Okay. Now I know it would be ICC ID, for example, and I copy and paste the ICC ID here. Disable result is okay. So if I again do get profiles info, I can even grab state. Now it's disabled. And if I would now basically do a equip, that will basically restart logically pySim, but I could also, equip. I could also stop pySim shell and restart it. Interestingly, we still have a uSIM active. I guess I need to do a reset first. Now an equip. Still there. That's surprising. I would have expected the uSIM application to disappear because there is no active profile anymore, but maybe this eUICC has some voodoo magic happening. Maybe that, no, it's the profile is disabled. That's weird. The profile is disabled, so there should be no uSIM application on this card. Let's try select adf.usim. Sorry, typo. Yeah, actually works. That's really weird. Okay. So apparently this vendor decided that when no profile is active, they put in some fake profile with a fake IMSI that's all zeros. I haven't seen that yet. I haven't seen this on another eUICC where I tried this. So, okay. That is a bit strange, but it's an implementation detail. That's nothing in the spec that would mandate such behavior. Okay. So yeah, so we can, if there is an active profile, I mean, we can do the other operation. We can go, for example, select ADF ISDR, and then we can again list. No, actually, we can go back to the disable profile, and we can just turn that into an enable profile. And now let's, to be safe, I'll reset the card. So now we're actually getting a 262.24 IMSI. So now we have an actual usable profile with a reasonable IMSI active on this card. And what you can see from this, if you've worked with SIM cards before, classic SIM cards, that basically once a profile is activated, you can use it just exactly like a SIM card. And I could now take this eUICC and insert it into any phone as long as it supports uSIMs. A classic 2G GSM phone without uSIM support would not work, but a uSIM supporting phone, so that's later GSM only phone or phones from the 3G era onwards, you could just insert it and it would just treat it like a normal SIM card, and it will always use the profile that's active at the moment. And then you can remove it, put it again in a smart card reader, change a different profile, download a profile, whatnot, and then you can again put it back in a device, even a device that doesn't support eUICCs or eSIMs. So, okay, let's leave here before I forget that this is running in the background. So this was a quick demo of what you can do with pySim shell. So you can explore a bit, you can switch profiles, delete some, and do things like that. You cannot download profiles from pySim, at least not today. We will do that with lpac later during this talk. Getting to the LPA, so the local profile assistant, as I said, it's the software that runs on the user equipment. It can also be fully built into the eUICC. That's an option. It's called the LPAE in this case. That means that all of the software is in the chip itself, and it uses open channel and features that allow SIM cards to directly speak TCP/IP based protocols on the mobile data connection. I don't have any hands-on experience with this. So the standard case with smartphones is the so-called LPAD. That's the LPA on the device, meaning that your Android, your iOS, whatever you use, has some a software called LPA that implements these interfaces as defined by GSMA for the eSIM universe. So it talks to the eUICC on the one hand side, that's the chip card, and on the other hand, it talks to the SMTP+, the backend infrastructure. So the SMTP+, as I said, the subscription manager data preparation enhanced, that's the plus. Without plus, it would be machine-to-machine eUICC. It basically is that, and it combines some features. So yeah, what does it do? Really the most, let's say, I would say the most prominent function is the so-called profile package generation and binding, protection and binding. So we have the unprotected profile package. That's something like the profile package that we looked at with Python earlier on in a DER format. So that's plain text, unencrypted, unsigned. It's the raw ASN1 data that describes the eSIM. And then there is a process called profile package protection, which encrypts the eSIM profile and puts a cryptographic MAC checksum, and it also segments that in chunks of 1020 bytes for whatever reason. Why it is exactly 1020, I don't know. Just says in the spec. And then there is a process called binding, which results in the bound profile package. This then means it is bound to one specific eUICC. And once it is bound, it can be downloaded to the eUICC, and then the eUICC itself will extract that bound profile package. It will do all the signature validation, and it will create the file system that's described in it and apply all these other parameters. And in the end, you will have one additional eSIM profile on your card in this process. This is then the profile package delivery here. And there's some other features which I'll skip here. I'll also skip the SMDS. So what kind of interfaces do we have? That's where it starts to get interesting, and we will look at those later on. So we have the ES8+, ES9+, and ES10B as the three interfaces that are relevant to download a profile into an eUICC. So here we have on the right-hand side the device, let's say your smartphone. The smartphone has an LPAD, the software on it, and you have the eUICC. The LPAD talks the ES10B interface to the eUICC, and it speaks the ES9+ interface towards the SMTP+. That's the server component running somewhere on the internet. And then we have sort of the ES10B and the ES9+ on both sides of the LPA. And through those two, there is tunneled the ES8+ interface, which basically goes directly from the SMTP+ to the eUICC. So this is the two-layer approach that is here. There's already some mention of the various cryptographic certificates here that are involved. They have a certain naming scheme. We'll not go into each and every detail here, just mentioning what this means over here. But yeah, all of this process is authenticated and so on. We'll talk about the security in some later minutes. So yeah, ES9 Plus. So that's again the left-hand side interface here, the outer left-hand side interface between LPAD and the SMDP Plus. It's an HTTPS-based interface over TCP/IP. The LPA is the HTTP client. The SMDP Plus is the server. And like any web browser or curl or wget or whatever web application, the client verifies the server TLS certificate. The only difference is that the server TLS certificate is signed by the GSMA. So it's not Let's Encrypt or some other certificate authority, but it must be signed by the GSMA. In theory, of course, it's the LPA software could also have a larger certificate store. That's an implementation detail. I'm just saying from the spec point of view, it should be a GSMA signed certificate. Yeah, there's no cryptographic verification or anything of the HTTP client at that level. So just like a normal web browser doesn't have a client-side certificate or some kind of authentication, it's just like a normal web situation. There's two different encodings for whatever reason specified on the ES9 Plus. One is a JSON-based interface and the other is ASN1-based. And now you would think, okay, or many people would think, well, let's ignore that ASN1 if there's a choice and just look at the JSON-based interface. Well, the JSON interface is just the outermost layer. And then in the JSON, you have fields that contain base64 encoded ASN1 DER. So you still need to deal with ASN1. So it's somehow weird that basically just the first layer of the hierarchical structure then is JSON suddenly, and then still you have ASN1 inside the JSON, so you need to deal with ASN1 anyway. So they might have just gone entirely for ASN1 and not introduced this JSON in here. I don't know why. So there is some additional rules that you won't see in normal HTTP usage about headers. So there's a specific xadmin protocol header that must be present and must have a specific value for both the request and the response. And also the user agent header is specified in a certain way or in a certain structure. And some other bits. Also content type is restricted. There's only two content types, one for the JSON, one for ASN1 permitted. But apart from that, it's HTTP 1.1, specifically no HTTP 2 in this context. So yeah, as that is just the outer layer, and then in that ESN9 Plus we speak ES8 Plus, but on the other side of the LPA, to the eUICC, we have something called ES10X, which is just an APDU-based interface, like basically any kind of smart card interface I've seen in 20 plus years. It's always some APDUs, and specifically it uses a global platform store data command as a transport mechanism. So basically the ES8 Plus data that gets sent here through the ES9 Plus tunnel gets segmented in APDU-sized chunks, meaning 255 bytes maximum, and then gets sent as stored data into the eUICC, and the response goes inversely the same path. So I already spoke about certificates. This is the certificate chain, at least the simple one of version 2 eSIM consumer described here. So, and the relationship and what happens where. The important bit to take from this graph is that every part basically has certificates. So we have the certificate issuer with its certificate authority at the root of trust. That's the GSMA, or respectively the service company that GSMA contracted to do this. And they are based on the policies and the security requirements, which are quite strict. They issue certificates for eUICC manufacturers. Those are the guys producing the eUICC chips. And they, in turn, using their certificates and private key, they are able to generate certificates on each eUICC. So every eUICC has an X509 certificate and associated private key, which uniquely identifies this eUICC, and the certificate name includes the EID of the eUICC, and that is signed by the EUM, and the EUM certificate is signed by the certificate authority. And on the server side with the SMTP+, it's basically the same. The SMTP Plus needs not just one, but three certificates or three sets of certificate and encryption or the secret key. And all of those get signed by the GSMA. And then in the ES8 Plus interface, we have a mutual authentication between those parts and certificate verification. So the eUICC receives the certificate from the SMTP Plus, and using the root certificate, which is stored on the eUICC, it can validate that the SMTP Plus is authentic. And likewise, the SMTP Plus receives the eUICC certificate and the EUM certificate, both here over the ES8 Plus, and it can then in turn verify the chain of trust and verify that it is an authentic certificate signed by the GSMA root of trust. We also have more certificates, but let's keep it like this. In later versions of the specification, there's multi-level certificates, so they can be intermediate certificates in the hierarchy. Here it's rather flat, so the level of depth is maximum basically 2 here, but in later specs it can be a more complex situation with sub-certificates. And this entire certificate dance, together with the certificate, the CA policy and the GSMA requirements, is what makes it basically impossible for any random user to just create their own eSIM profile, because in order to do so, basically they need one of these guys, the SMTP Plus. And in order to get the certificate from the CI to operate an SMTP Plus, you need to go through extensive certification. This is the eUICC side. It's the same also to manufacture eUICCs that work in the GSMA consumer or any of the other eSIM systems. You need to have extensive compliance processes and audits, and the operating system needs to be according to EAL4+, and yeah, lots of requirements on all parts of the physical access security, the business processes and everything. So a lot of compliance stands. Likewise, on the SMTP Plus, it's the same. I think the costs, even if you manage to achieve to fulfill all the requirements in the first step, the cost of the certification is in the order of, I think, about 27,000 euros for the initial certification, and then about 14 or 16,000 euros every year on average for the re-audits that you need to do. So quite a significant cost only for the auditing. Of course, that doesn't include the cost for developing it and for establishing and documenting all the processes in line with the policies, so you can actually get accredited. So yeah, a lot of security processes involved. So in the end, what happens on such an eSIM? Well, we have the remote provisioning. That's the actual download. We have profile management, such as enable, disable, list profiles, delete them. That's we also looked at this earlier. And we can retrieve the EID. We also saw that. There's also a memory reset function that basically is supposed to get the eUICC back in the state in which it was delivered, removing all the profiles or any other configuration, basically a factory reset option. Yeah. And you can, yeah, also store some default address of which SMTP Plus should be contacted, but that's not really necessary in the end. Yeah, lots of details about the processes. I will not go through those ladder diagrams. Those are from the spec. I skip those. This is too much detail for now. We'd rather look at this in the protocol trace and have a brief look at it. Yeah, so in terms of open source software, what can you do? Well, technically, all the protocol specs are public. So you can implement all of that in open source software if you want. However, if you want to work within the GSMA universe, meaning you want to install a profile on a commercial production GSMA signed and certified eUICC, then you can have all the software you want. You will not have the certificate to actually authenticate against this device. And likewise, if you want to build your own eUICC or emulate one or something and play in the GSMA consumer eSIM system, you will not get the certificate for the eUICC. So again, you cannot really, technically you can implement all of it, but you cannot play because you in the club because you won't get the certification. What you can do is, I think there's a separate slide on this. So let me stay on this slide before we switch. The LPA is sort of the only part of the software that you can develop as open source and use it with the production GSMA system, because as I mentioned before, the LPA does not authenticate itself with any kind of certificate. It just connects as an HTTP client to the SMTP plus and then verifies or verifies not the signature of the TLS certificate of the HTTP server. So this part can be implemented as open source, and there's actually multiple implementations. I have two examples here. One is the LPAC that we will play with in some minutes, and there's also the TruePhone LPA desktop. The first one is a C command line program, and the second one is a Java GUI program. Guess which one I'm using? If you know about me, then I don't need to answer that question. So in IoT, well, yeah, let's ignore that. That's not the topic for today. So yeah, what you can do though, well, if you actually build your own eUICC or obtain one that uses your own certificates from a private root of trust, and then you can, of course, issue all those certificates yourself. So you can issue certificates for the eUICC, you can issue certificates for the SMTP+, and you can run all of that. It will just not work with any third-party eUICC or third-party eSIM profiles. So you can run all of that and technically make it work, as long as you don't need operational interoperability with the GSMA system. And that's actually what I did with the so-called SGP26 key material. So GSMA has released a specification called SGP26, which contains test certificate data and OpenSSL commands on, excuse me, OpenSSL commands, how you can actually create certificates that comply with all these requirements in terms of additional attributes and how the subject keys or the CNs are structured and so on. So basically, you can take those certificates, and there are some vendors that offer test eUICCs, which have again installed the certificates and keys that are documented in this SGP26. Of course, you won't have any security in this SGP26 situation because SGP26 also includes the private keys. So anyone can create certificates and sign everything. So it's completely insecure, but for testing and development and exploring the system, that's of course fine. If you want something in between the GSMA club and the test certificates where everybody has the private key and everybody can issue certificates, you can go for a private CA. So you could operate your own certificate authority, and then only you have the respective private key material, and only you can issue certificates and not anyone else. So that's the compromise in between. So I implemented the minimal proof of concept of the SMTP plus called osmo-smdpp. The additional P is for plus, like we have CPP for C++. And it's currently part of the pySim Git repository. That might change later. I might split that out, and it implements this ES9 Plus interface, only the JSON variant for now. I have some untested patch for the ASN1 variant. Once that is tested, I will merge that as well. It's in the end, it's not all that different, as I mentioned. It's only the outer layer, and then inside, it's again ASN1 anyway. It implements this bearer secure, no, BSP, the something security protocol. I forgot what the B was for. I sometimes also forget acronyms. So that's basically the profile protection and binding. used to be called SCP-03T. I remember that one, but I don't remember what BSP was exactly. And it's ESA Plus. So it does all the steps that are needed to download an eSIM into an eUICC. It does not do many things, but let's first look at why. Well, why did I develop this? It was really just for fun. Because I always think any kind of technology or protocols should have open source implementations, and also in a practical sense, the GSMA specifications are actually they are vague or unclear. Sorry for that. In certain points, that was also confirmed to me by several other people who have implemented these protocols, and they all say it's very difficult to get it right because it's not very clear, and also specifically because the GSMA specs don't contain any test vectors. So you have cryptography with, let's say, non-standard formats for how ECDSA signatures are encoded over the wire, and you have absolutely no test data. And now with the osmo-smdpp working, anyone can basically generate their own test data and can understand how this is supposed to work. Yeah, other people do Sudoku or crossword puzzle. I just thought this was an interesting challenge to puzzle all this together. It's also for sure the project that involves most crypto from anything I've developed so far. I'm not a crypto nerd, so it was interesting to really go from using X509 certificates to really understand how they are built and how you verify them, and how elliptic curve key agreement works, and how all these things get put together. So the status, well, the mutual authentication works, the profile download works, and there's lots of gaps in terms of a real-world implementation. For example, there's no personalization there, meaning that it's always the identical profile with the identical ICC ID, the identical IMSI, and the identical keys that gets downloaded. So every time you want to change that, you actually need to manually edit the file containing this unprotected profile package that we looked at earlier. So fine for lab use, but not really for, let's say, a private network where you want to issue a couple of dozens or hundreds of eSIM profiles. A certificate verification, embarrassingly, is not implemented yet. Well, I have some code now for the verification, but it's not integrated in osmo-smdpp+, so that will also be merged soon. And none of the other interfaces that are not critically required have been implemented so far. And now, with that, thanks for staying with me through this tour so far. Let's look at actually running this. So I will now remove the commercial production GSMA eUICC and insert the test eUICC in my smart card reader. And I will switch to a different screen. So at the bottom, I have a shell where I will run the local profile assistant, the lpac program. Let's just run that. So we see right now on this, we call profile list, and it outputs some JSON that I've put through a pipe through a JSON pretty printer here. So we basically see, well, right now there is one profile installed and it's a test profile. Well, it's a test eUICC, so it comes with a test profile pre-installed. And the profile is in profile state 0, which, well, is that enabled or is it disabled? If we want to know that, we could either look at the specs, or we could just again use pySim, because pySim decodes that in a more meaningful way. I guess it's enabled because we see a usim here, ifdir, but let's see. Get profiles info. So that basically performs the same. No, it's also disabled. So okay, this card also has a usim application, even though the profile is disabled. Yeah, so it's disabled. So 0 means disabled. So it's a logical way to do things. So what I'm now going to do is I'm going to start osmo-smdpp up here. Takes some time. Now it runs. It's running on port 8000 and with HTTP without TLS, and I'm running a, I think, Nginx in front of it as a TLS proxy, TLS reverse proxy. So the lpac can speak HTTPS to the Nginx, and Nginx will do plaintext HTTP on localhost to this SMDP+ that I just started here, the Python program. And what I can now do is copy and paste the correct command from a shell window that you do not see. So yeah, I can do something like this. Actually, do it like this. This is how it would look like also if you try to reproduce this. So I'll just start this. It will spew lots of data on both sides. We will then scroll back and look at it in detail, what's happening. So as you can see, it takes quite some time. What you can see at the bottom right now is hex dumps of the APDUs that get sent to the eUICC. And you can see it takes quite some time, and the eUICC is busy because it needs to do all that ECC crypto and write, create a file system and commit a lot of stuff to non-volatile memory and make sure this is all committed and so on. So the profile installation actually takes quite some time. And in the end, well, this is a mix of the hex dump is something I patched into the code so I get the APDU hex dump. And here we see the final result. It says success. Well, that just, don't let that confuse you. Success means that this profile download that we issued here was successful at the level of the ES9 Plus interface. It doesn't mean that at the ES8 Plus that's tunneled inside it actually was successful. In order to understand whether this was successful or not, we actually have to do list the notification. Well, just look at the normal output. So what we do, we list the notifications in the card. So we see there's multiple notifications pending. I didn't delete some old ones. So I use the sequence number of the most recent notification. And I say process, I think was the name, 65. Again, redirecting all my debug output to dev null so it doesn't confuse us here. So now basically, using this command, the notification, which contains the actual result at the ES8 Plus level, was sent to the SMDP Plus. Basically, we see this output here, and it says profile installation final result is a successful result with this AID and whatnot. So yeah, it was a success. So only once that notification gets delivered to the SMDP Plus, we can make sure we can know that it actually was successful. And actually, we should remove those old notifications that are still on that card, also the 61. So the local profile assistant typically does poll the eUICC if it has notifications. So it performs this operation frequently. And if the result is non-null, so there are notifications pending, that those notifications get processed, means they get sent over HTTPS to the SMDP Plus. And that is an ongoing process all the time. It's just this lpac implementation doesn't do that automatically. You have to do this as a user for research and testing. That's, of course, not too bad. So now let's look a bit at what happened here during the download. You see lots of dumps, hex dumps, and so on. So what we see here is the first JSON request that arrives. You see there's an eUICC challenge that's base 64 encoded. The two equal signs at the end give it away. We have the eUICC info, which is again base 64 encoded data structure with ASN1 inside. And then we print the decode of that. So we actually see, well, this is the version number and the supported PKIs and so on. So the eUICC info that was sent here. By the card, and then this is the response that we're transmitting in the reverse direction, and then the next HTTP request with more data happens, and so on and so on. So this is not very useful to decode. So what I can show you is there's a JSON viewer program Where is it in? It gives us a hierarchical decode of the JSON. This is the eUICC info part of the initiate authentication request. And we see here the eUICC info 1 that we also saw in pySim earlier that gets transmitted to the server, and it contains the list of PKIs that are allowed for signing and for verification. In this case, it's 2 different certificates. It's 2 different elliptic curves. One is the NIST P20 P256, and the other one is a Brainpool P256R1 curve for root certificate. So that is the content of that first request. And if we look at the answer, just a second. Should be this here. That's the SMTP signed. So we see it's rather simple. This transaction ID, the eUICC challenge that the eUICC sent, the server address and the server challenge. This is a challenge response-based authentication algorithm. And then using all this data, the client can perform the second step of that mutual authentication process, which then looks like authenticate client. There we go. So that's another ASN1 that I'm just representing here as a JSON in decoded form. So we have the data from the eUICC again containing transaction ID, server address, and the server challenge. So that gets sent back to the server, plus the eUICC info2 data structure, and all of that receives a cryptographic signature, an ECDSA signature, and using that signature and the certificate, which is here below, that's the eUICC certificate, the SMTP Plus can verify that it was signed by an eUICC, and that certificate again can be traced back through the EUM certificate to the GSMA root certificate, and that way the SMTP Plus can establish the authenticity of this eUICC. And this then continues. I'm not going through all the different steps, but what I will show you next is the actually the bound profile package that in the end gets downloaded to the that's especially the eSIM profile, which consists of multiple different steps here. Each of those is long. So at the bottom, these are 1020 bytes for each of those. So we have a first sequence of 87, sequence of 88, a second sequence of 87, and a sequence of 86. Literally, they call it this way in the spec. They didn't come up with a more meaningful name. Actually, the name of the data structure is called by the binary encoded tag value that is used in the encoded format. So it's a bit weird. But anyway, so that's basically all the encrypted and signed data, and specifically this here at the bottom is the actual eSIM profile that gets downloaded into the device. And as we have seen, this was successful. So what we can actually do is we can now again list the profiles here at the bottom. And we see now there's 2 profiles. This is the original test profile that already pre-existed. And then now we have this OsmoCom profile here at the bottom, which is new. So a second profile has been installed on the device. If I would retry this process again, then it would fail. Well, it would succeed at the ES9 plus level, but then the notification about the ES8 plus would tell us it has failed, because remember, the SMTP Plus doesn't do profile personalization, so they all have the same ICC ID and so on, and the SIM card will basically say, well, no, I already have this profile, I cannot install it a second time, I already have this. So we first either need to change the data at the SMTP Plus side to have a different ICC ID, or we delete the profile here from the card before we can download it again from the SMTP Plus. And of course, likewise, the same we could do in pySim. It would, of course, show us the same output. Yeah, so that was the demo for that part. Now I could also do a demo against the production SMDP Plus with lpac. Of course, we don't get logs from the production SMDP Plus, but maybe we stay with this setup, with the test setup, in case somebody still wants to see something before we do that demo against the production one. Yeah, any questions, comments at this point? I know it has been a long talk, but yeah, I try to cover the foundation to understand the part that I have demoed here. So the question is, where does one acquire the test eUICCs which you can use your own CA with? Well, the test eUICC you can actually use the SGP26 CA. So it's the CA where everybody knows the private key, the completely insecure one. One manufacturer is Comprion that sells test eUICCs. And I'm currently working on creating those also at Sysmocom. So hopefully in some weeks or a month or so, we also have test consumer eUICCs available in the Sysmocom webshop. Apart from that, I'm not aware of other sources, but in the end, I would guess you can get them from any eUICC manufacturer. The question is just whether you would be interesting or relevant enough to the eUICC manufacturer to get such test devices from them. So I see some typing in the chat. So I'll wait. Maybe there's an additional question. Maybe use the interim that Sysmocom will also be offering eUICCs with private CA. So basically, yeah, outside of the GSMA, but not in a way that everybody can sign eSIM profiles with that. So the details of that are yet to be determined, but definitely we have that capability of personalizing an eUICC OS on a chip with arbitrary certificates. So we could even do customer-specific eUICCs with whatever certificate they want to have on recognized by those cards. Okay, since there's no question, then I can go to the next demo with the production eUICC. So I will put a Sysmo eUICC 1-C2G in the reader slot. That's our production eUICC, which has GSMA certificates on it, so we can use it with any random eSIM profile out there. You cannot install your own eSIM profile because, well, yeah, it's part of the GSMA club only. So let's just quickly look at that eUICC and what profiles are installed on it. So there's one profile on it right now. It's a test profile, but a test profile that's signed by GSMA. That's actually something we pre-install on the Sysmocom eUICCs. So you can have an eUICC, even though you cannot install your own profiles. You can only install, let's say, commercial eSIMs, but at least you have one profile on it which has a 00101 IMSI on it for test use cases in private networks and so on. So yeah, and on this one we can now install then get eUICC info. Just yeah, so we see again subject key identifier. I recognize this is not the test CA route, so it must be the GSMA production. certificates. We can of course double check that with the certificates, but for now it's just trust that this is the case. So how do we actually download a certificate on this now? Well, what we need is, if we look at this command here earlier, we need to know the SMDP plus host name here. That's what we pass here. And this is the so-called matching ID. So the SMDP plus is the server from where we download, and the matching ID is basically some kind of token which tells the server which eSIM profile we are to download. And already in preparation of this talk, I purchased an eSIM profile from Red Team Mobile. Could have been any other eSIM vendor. They just have the cheapest profiles, I think, for these kind of tests. Things like $1.09 or something like that for an eSIM profile that has 1 day of data traffic. So that's rather affordable. So I have bought the profile, and you get this this QR code with the when you purchase an eSIM profile, a consumer eSIM profile. Now let me try to find where I stored this and open it quickly in a viewer. Yeah. So please don't activate it right now, otherwise my demo won't work. So this is the profile I bought for US dollar 109. I made a big expense for that. Now, how do we actually get this SMDP plus code and the activation code from this? Well, we can use a what was it again? Oh, I forgot again the command line tool for that. Too much. And yeah, you can basically use any tool for decoding the QR code. I could use my smartphone, but yes, it was exactly the Z-bar image. I'm going this way, so I'm getting the decode here. So the actual QR code contains this string, so it's LPA colon $1 RSPU and so on. So between those first two $signs, that's the host name of the SMDP plus, and after the last $sign, that's the activation code. So I can copy and paste those into my it was -s, I guess, into my command line over here. Hopefully nobody has, of the guys watching this, has used this yet. I will save the log file of the communication. So yeah, again we see slow progress. That's a good sign. If there's an error, usually it aborts relatively quickly. Well, it says success here, but as we know, that's just the success at the ES9 plus layer. So we again lead this notification list. So we have one well, JSON pretty printing makes it more readable. So the sequence number is 0. This is the first time this card was used. So what I can do now is lpac notification. Well, actually, I would have to decode it locally. Of course, I'm now sending the notification to the server without seeing locally how it how it looks like. But anyway, for good matter, let's forward this to the server so the server knows this was delivered. Maybe later on we can also do a local decode of what we've just sent, in case that's interesting. I'm starting pySim shell here again on this device and do a get profiles info. And here we see, well, this above there, this is the test profile that was already there. And now we have this new Redti mobile profile. Now let's enable that profile. Wrong profile re-enabling. That's interesting. The other one, the other one is enabled. Yeah. So as long as the test profile is enabled, of course, we cannot enable a second profile. I mentioned this earlier, so we need to first disable profile, the test profile. Now we can enable the other one. Now it's okay. Yeah. Okay. Guess we need to reset the card. Yeah. Now we can enter the eSIM ADF. Actually, let's use the full screen size. And now we can and we see now this is a production IMSI 23210 of the eSIM profile that we installed. And of course, I could put this in a phone now, and it should register to the network and use that subscription, the $1.09 subscription from Redti Mobile. So that's it for that demo. Any further questions? Do you want to see something else? Yeah, you're welcome, Max. Max said he has to go. Am I doing these experience on cards in simply form factor, MFF2 or so that kind? It's really the normal plastic card form factor. So it's a normal smart card that I'm using here. What's the typical experience if you don't send a notification to the SMTP Plus? The experience is that you can download the profile again and again because it's not yet downloaded. Does the operator use it to activate the account? Most likely, yes, because the ES2 Plus interface, that's the interface between the operator and the SMTP Plus. That's basically what happens in the background. So I went to the Redti Mobile, but of course it works with any other. I don't want to advertise for them really. That's just for testing. I mean, I don't even want any data or any subscription. I just want an eSIM profile to test my software with. What happens is basically when you order an eSIM profile somewhere using whichever method, the operator or the website that you purchase it from will actually send an ES2 Plus request to the SMTP Plus to create such a profile, and the activation code will be returned back, and the activation code will end up in the QR code that goes to you. And once the profile then has been successfully downloaded, and then the notification goes back, the ES2 Plus interface notifies the operator of that successful installation. So I suppose the business logic at a regional operator would only activate the profile after it has been successfully downloaded into an eUICC. But how many of them do that? Or I, of course, have no idea about that. But I guess that's the way how it's supposed to be. I haven't done any related testing. That's not really the part that I'm interested in, but I'm sure there will be plenty of security people playing with that and seeing whether that actually is done properly or not. Okay, well, meanwhile then, maybe until some other questions are there, we can also decode that pending notification message that we had here, just so we see what we actually sent to the server. Again, it's one of these JSON. So we see this is the API endpoint that it was sent to, this handle notification URL, and this is the JSON data that we sent to it. And the JSON data contains one element, and that's the pending notification, which is a base64 again encoded string. So what we can do here is we can again go in Python, import base64. Actually, let's do it differently. From base64 import b64 decode. Then we can basically do from pysim.decode eSIM.rsp import no. So then the next thing we have to do is we need to check I don't recall that in detail. So yeah, the type name of the pending notification is pending notification, but with an uppercase P. So lowercase is always the name of the field, and uppercase is type in ASN1. So okay, now we know that. So what I can do now is I can do a rsp.asn1.decode pending notification. That's the type name we want to decode, and as parameter we do b64 decode, and then that not that string, but this string which we received here. And well, let's do a well, yeah, it's not import JSON. JSON doesn't do the bytes from pprint import pprint as pp. Let's wrap that in a pp for pretty printing and increase the. So what we actually see here is the what we return to it. So it's a successful result. And yeah, the ICC ID here that was installed, notification address. Yeah, I guess the only really relevant part is this one here. It's a success result. So there's a question, just to confirm, is it possible to use this method to install a profile to easy.e card, for example, or any other commercial chip? Yes, that is correct, even though for eSIM.me, let me add that for correctness or for completeness, you violate their terms of service. So eSIM.me sells those cards under specific terms, and those terms explicitly indicate that you are legally not permitted to use any third-party software. You must use their software, so their LPA, and not any third-party software. So in theory, it should be possible, but the test I did here was using a Sysmo eUICCC-C2G, but you could use any GSMA compliant eUICC with this method in general, right? It's just with eSIM.me, there are these terms of service that you need to double confirm when you order something. So that's why I didn't do it with this card here in the demo. The Sysmo eUICC C2G, let me just type that in the chat. It's not really is a product we are shipping samples at the moment at Sysmocom, and that will become available. So this first production batch right now going on of 1,000 cards, and those will be also available in the Sysmocom web shop once that production arrives. And we don't have these kind of terms, so you can use whatever software you want without violating any terms of services. But yeah, I mean, you could also, of course, if you're skilled enough and you know which chip on a smartphone or whatever device is the eUICC, you could unsolder it. You could put that in an adapter, for example, if it's MFF2 form factor in a solder type adapter or CIF socket adapter, and attach that to a smart card reader. That would also work. I mean, that's the point is basically every GSMA certified. So basically, every eUICC that requires a GSMA certificate must support all of these operations and protocols. That's sort of the condition of the certificate policy. So you would violate the GSMA rules if you created eUICCs with GSMA certificates that do not understand those standard protocols. So I doubt anyone would do it, because I guess they would risk that they would end up in the certificate revocation list of GSMA. I don't know of any precedent, but at least how the theory works, that's my understanding. I guess it should work with any consumer eUICC from any vendor. But of course, GSMA doesn't say you cannot have terms of services that forbid people from doing that. Okay, good. I guess that means we have reached the end of line. Yeah, I'd like to thank Chris of Mode 51 Software. He has done a nice job of explaining a lot of these things in his blog posts and responded in numerous private emails where we exchanged some traces back and forth that whenever I was stuck with my interpretation of the GSMA specs. So that was very useful to have his help and support. And then also, of course, all the people who did the Python modules I'm using, like ASN1 tools, the Klein web server, cryptography, PyCryptodome, and so on. And that brings us to the end. There's a further reading slide. So this is the blog post from Chris that I mentioned, the GSMA list of accredited eUICC manufacturers, the eSIM white paper of GSMA, and the first one is the talk I mentioned, the demystifying eSIM technology talk that I gave in last summer at the CCC camp. And with that, we have reached the end of the file. And